Hello everyone, welcome back to this series on solutions to previous year GATE chemical engineering questions. In the previous video, we were looking at chemical reaction engineering questions from GATE 2024. In this part, that is part 2 of this series, we'll be looking at 2-marker questions from GATE 2024 related to chemical reaction engineering. So let's look into the first question. A first order heterogeneous reaction A giving B is carried out using a porous spherical catalyst. Assume isothermal conditions and that interface diffusion controls the reaction rate. For a bulk concentration of 0.3 moles per liter of A, the observed reaction rate over a 3 millimeter diameter catalyst particle is 0.2 moles per second liter of catalyst. Now, for a bulk concentration of 0.1 moles per liter of A, and the diameter of catalyst being 6 millimeter, what will be the observed reaction rate? So first, let us note down the given parameters. We have first order reaction A giving B. The reaction is controlled by pore diffusion or interface diffusion. The two scenarios are as follows. In the first case, we have Ca1 is equal to 0.3 and D1 is equal to 3 millimeter. Rate is given as 0.2 moles per liter of catalyst into second. What will be the rate for a concentration of 0.1 moles per liter and diameter of catalyst being 6 millimeter? Now, firstly, the observed reaction rate is given by this expression Kca into eta. Here eta refers to effectiveness factor. Since the reaction is pore diffusion control, the effectiveness factor will be equal to 1 by Thiele modulus. So it is well known that for negligible pore diffusion effects, eta will be equal to 1, whereas for strong pore diffusion effects, eta will be equal to 1 by Thiele modulus. Thiele modulus is given as L into root K by D, where L refers to the characteristic length of the catalyst. So since the other parameters K and D remains unchanged, we can write rate as directly proportional to Ca from the rate expression and as inversely proportional to Thiele modulus from the definition of effectiveness factor. Hence, expanding these conditions to the two scenarios and taking the ratios of the rate of the reactions, we get Ca1 by Mt1 divided by Ca2 by Mt2, which is further written as Ca1 by L1 divided by Ca2 by L2. Now, for a spherical catalyst, we can write characteristic length L as R by 3. So this is because L is basically ratio of volume to the surface area of the catalyst particle. So since it is a sphere, we have volume as 4 by 3 pi r cube and surface area as 4 pi r square. On taking the ratio, we get L as R by 3. Now substituting the given values for Ca1, R1 and the radius of the catalyst, which is given in terms of diameter. So we get R2 as 0.033 moles per liter of catalyst into second. So option B, 0.033 is the right option for this question. So let's move on to the second question. A first order liquid phase reaction A giving B is carried out in two isothermal plug flow reactors of volume 1 meter cube each, and these are connected in series. The feed flow rate and concentration of A to the first reactor are 10 meter cube per hour and 1 kilomole per meter cube. At steady state, the concentration of A at the exit of the second reactor is 0.2 kilomole per meter cube. Now, if we were to replace these two PFRs with two equal volume CSTRs, what will be the volume of each CSTR to achieve the same overall steady state conversion? So let us note down the given parameters. So we have two PFRs in series. So equal volume 1 meter cube. The inlet consists of A with concentration 1 kilomole per meter cube, and the volumetric flow rate is 10 meter cube per hour. The exit condition is given. Ca will be equal to 0.2 kilomole per meter cube. Now, considering case 2, which is a system of two CSTRs in series of equal volume and same inlet and exit conditions. So we need to find the value of V. So let's look into the solution to this question. Now, for two PFRs in series, the design equation is given as sum of volumes of each reactor divided by Fa naught, which is the molar flow rate, will be equal to integral 0 to Xa dxa by minus Ra. So since the reaction is first order, we can expand minus Ra as Kca naught into 1 minus Xa. And in the LHS, we can write Fa naught as product of concentration of A into volumetric flow rate. Further, on simplification, basically cancelling out Ca naught on both sides, we get V1 plus V2 divided by V naught is equal to 1 by K integral 0 to Xa dxa by 1 minus Xa. So here, Xa is equal to 1 minus 0.2 divided by 1. So hence Xa will be 0.8. So further simplification and integrating the expression, we get 2 by 10, basically the sum of two volumes, which is 1 plus 1. So divided by V naught is given as 10, is equal to minus 1 by K ln 1 minus 0.8 by 1. So on simplification, we get K as 8.047 R inverse. Now, for two equal volume CSTRs in series with a first order condition, we have the following design expression. Tau will be equal to Ca naught V by Fa naught, which is equal to 1 by K, Ca naught by Ca, whole power 1 by N minus 1. Here, capital N corresponds to the number of CSTRs in series. Now, expanding Fa naught as Ca naught into V naught and substituting the value of capital N as 2, we get this expression. Further, on substituting the values of Ca naught, V naught, and rate constant, as well as the number of reactors in series, capital N, we get volume of the reactor as 1.54 meter cube. So hence the right option to this question is option A, 1.54 meter cube. Let's move on to the next question. The residence time distribution E for a non-ideal flow reactor is given in the figure. The rate constant for this reaction is 0.2 minute inverse. The reaction is first order. The inlet concentration is 2 moles per liter. What will be the exit concentration of the reactor? So let's note down the given parameters. The reaction is first order and K is equal to 0.2 minute inverse. The inlet concentration of A is 2 moles per liter. We need to find the exit concentration of A. We have been given the residence time distribution, which is a graph of E versus T. Let's look into the solution to this question. So it is a well-known fact that the area under the curve of residence time distribution is 1. So which is basically the area of this rectangle given in the figure. So as we all know, area of rectangle is basically length into breadth. Here length is E, which is unknown. Breadth is 5 minus 3 units, which is 2. So hence substituting this in the expression of area of rectangle, we get E into 5 minus 3 is equal to 1. So we get E as 0.5 minute inverse. Now for real reactors, the design equation is Ca by Ca naught is equal to 0 to integral 0 to infinity Ca by Ca naught of ideal reactor into E dt. For a first order reaction, we have Ca by Ca naught ideal is equal to e power minus kt, which is a well-known a well-known result obtained for a batch reactor for a first order reaction. Now, substituting this expression in the given real reactor expression, we get Ca by Ca naught is equal to integral 0 to infinity e power minus kT into e dt. Further, we can substitute the value of E, which was found as 0.5 minute inverse, and the integral 0 to infinity can be reduced to integral 3 to 5. That is because before 3 and after 5, the value of E will be 0 as per the given figure. So hence we have 0.5 integral 3 to 5 e power minus 0.2 t into dt, as k is given as 0.2. On substituting the value of Ca naught as 2 and further integrating this expression and simplifying, we get Ca is equal to 0.905 moles per liter. So hence option A, 0.905 is the right solution to this question. So with this, we come to the end of the chemical reaction engineering related questions from GATE 2024. Stay tuned for the next part, wherein we will be looking at the chemical reaction engineering questions related to GATE 2023. So if you like this video, please share and subscribe to the channel. And we will see you in the next part. Thank you.